Good afternoon to all of you. Today we'll be studying about oscillations. Before we speak about oscillations, let's get an idea what a periodic motion is. It's a motion which repeats itself, or rather, to be more specific, a motion which repeats itself at regular intervals of time. The most famous examples are, of course, the Earth revolving around the Sun. Then you have seen a tuning fork vibrating. Then a spring, when released, makes oscillations. Then when you pour liquid into a tube, you can see that it is oscillating. And of course, the pendulum. Now, in a special case, when the periodic motion is confined to a well-defined limits, and we call the well-defined limits as extremum position, okay? Extremum position. So, it will be either a higher point than the equilibrium or a lower point to the equilibrium. Such motion are called oscillatory motion. That is, a motion is effectively a to and fro motion. So you can see that here the tongues are making a to and fro motion. Here also spring is making a to and fro motion. Okay. Here also the liquid is making a to and fro motion. The pendulum also. But then you can see this is not a to and fro motion, this Earth moving around the Sun. So now we can conclude that all oscillatory motions, these are all oscillatory motions. To and fro motions are oscillatory motions. These oscillatory motions are periodic, but not all periodic motions are oscillatory. Now we'll go into simple harmonic oscillations, okay? Simple harmonic oscillation, or rather we just call it as SH. So we'll just take up the example which I'm going to show you here. You can see I have pulled a spring which is attached to a block. Now it's being released. Okay. Now look, it's entered a new point. This is the equilibrium position. Here it's the equilibrium position. Now when this is an extremum position, okay, it is at a distance x. So when you release it, it's going to another extremum position, that is a minimal position. Okay. So with this example, we'll just deal with the oscillator. So you can just see that. So once you pull it and release it, what happens? There's a restoring force trying to come back to the equilibrium. So first point we can note from this is that the restoring force acting on the particle at any instant is directly proportional to the displacement. So how much x is going, how much you pull it this side, x, that much itself it's going to the other side. The second point is the restoring force is always directed towards the mean position. So just imagine it's going to the mean position. So with this, we can write down the differential equation of a simple harmonic motion. So what is it? We saw that force is force. According to Newton's second law of motion, force is equal to mass into acceleration. So we know that here x distance is being covered. So in terms of x, acceleration is m into d square x by dt square. Okay. And this force is directly proportional to this x, but it is directed towards the equilibrium position. So that we can write m into d square x by dt square is proportional to minus x. Why? Because it is directed towards the mean position. Now, as always, what we can see is this can be written as m into d square x by dt square is equal to some proportionality constant, say k into x. So this can be rewritten as m into d square x by dt square plus kx is equal to 0. Now dividing through both by m, you can have m into, it's d square x by dt square plus k by m, x is equal to 0. Now substituting for k by m as equal to for k by m as equal to omega square, we take it as angular frequency. We can write the above equation as d square x by dt square plus omega square x is equal to 0. And this equation is known as the differential equation of a simple harmonic motion or simple harmonic oscillator. Okay, thank you. In the next video we shall discuss about its